Pete Yost here for the Unbuild It podcast. We have two sponsors this week. First up is Aero Barrier, a new way to air seal homes. Aero Barrier uses a blower door to move non-toxic airborne sealant into all the nooks and crannies where air leaks occur in a building's shell. It's a completely performance-based air sealing system. You get to watch your blower door number drop as the sealant tightens up your building. This technology was first developed for sealing forced air duct systems. And when I heard that the same company was developing a system to seal homes, I was really skeptical. But I have watched highly skilled Aero Barrier technicians prep a home and run the Aero Barrier technology, and it is clear that both the technology and the installation are based on sound building science and a superior understandings of how buildings leak air. The Unbuild It podcast is proud to have Aero Barrier as a sponsor. Check out their air sealing system at www.aeroseal.com. Our next sponsor is Home Building Crossroads, an educational webinar series sponsored by Zip System Building Enclosures and Advantech Subfloor Assemblies, bringing the best speakers in the industry to discuss building science and help you walk away with real solutions to the building issues you're facing. Christine Williamson, president of Building Science Fight Club, will present her course, Airtight Done Right, on 2 dates in December, Tuesday, December 15th, and again on December 17th. Airtight Done Right highlights small design adjustments using standard materials that architects and builders can immediately make to improve airtightness and energy efficiency in residential design. For more information and to register, visit zipsystem.homebuildingcrossroads.com. Welcome everybody to the Unbuild It podcast. I'm your prime host, Pete Yost, with Jake Grutten and Steve Bazit. And this episode is all about R. So you could say that this is our R-rated Unbuild It podcast.
Wow. You write
like
those
that?
quicker than anybody I know.
Man,
You've been a dad for a long time.
mine's like a
sound like he
steel
just made it up.
trap. So, welcome everybody. And given that this is about R, the heat is on.
I'm going to try to resist.
So Jake and Steve, how are we going to start off talking about? First of all, what do we mean by R?
I don't know. I'm trying to insulate myself from this conversation.
Ooh, Steve.
I can't believe that gets a chuckle and a clap out of Peter, but my I'm going to try to resist didn't get
Ooh,
a raise out of it.
Way
That
too
hurts my
sophisticated for
soul.
me. Jake, I totally missed that. Sorry,
Resistance to heat.
buddy. Yeah.
To the flow of heat.
Listen, if you
For
got
the
to explain your
conduction of
joke,
heat.
it's not a joke. You learn that in the sandbox, for God's sakes. Let it go.
I like the jokes that have to be explained. I also like the jokes that I'm the only one that gets.
Seems like we've had other episodes where you've made a joke and we've totally missed it, right?
Yeah, that happens.
You're
Pretty much all of them.
You're just a cut above us, Jake. That's all there is to it. So let's start off with the crazy thing, which is R is the resistance to heat flow. That begs the question of, well, how do we measure heat flow? And so that's the U factor. And so U is heat flow, and R is the resistance to that heat flow. And we're talking about conduction. So that's heat moving through solid things, as opposed to convection, which is heat moving through transported air or leaking air. So the first crazy thing is that
So, Peter, are you saying convection has absolutely nothing to do with, primarily has nothing to do with insulation? And I'm just setting this up for an argument I'm going to make later. So,
Well, I'm not
playing
surprised
the
to hear
lawyer.
that you were setting up for an argument, because
Me either.
what else would we expect? But we're
I'm trying to resist.
When you hang your head in disappointment like that, it's very clear that it's like 99% gray. Are they out of Just for Men in Boston all of a sudden?
yeah, but it's all hair. It's all hair for him.
Says the guy that needs a transplant.
Who, me?
I think he's talking about
I
me.
got-
a
oh, I
little
got-
Charlie
Is
Brown
that
thing
a
up front.
peninsula you got going up there?
We are not
right,
here
we can go
today to talk about our scalps.
Hey, he started it, just for the record.
Wow. This is supposed to be our most technical presentation, and it's gone right down the tubes. So here's the crazy thing, which is we are the only country in the world that uses to measure heat flow, British thermal units. And so, we have this crazy thing of BTUs per square foot per hour per degree Fahrenheit temperature difference. And that's how we measure heat flow. I mean, nobody uses British thermal units. They use hour, they don't use square feet, and they do a temperature measurement other than Fahrenheit. So pretty archaic. And here's the crazy thing, which is if our basic unit of heat flow is the BTU, where did that come from? Well, it's the amount of energy it takes to raise 1 pound of water 1 degree Fahrenheit. So the first thing is we picked a crazy ass unit and an incredibly tiny one to base the whole discussion of heat flow on. And then, of course, the reciprocal of the heat flow is the resistance to R value. So U is equal to 1 over R. Is that deep enough?
Very deep. Hey, I was going to say, just given our time of use, shouldn't we actually switch that from BTU to ATU, American Thermal Units? I'm going to propose that.
Even the Brits don't use British thermal unit anymore.
Yeah.
So, yeah, I think you're right on the money. It would be really confusing if we used US, and so it would be US TU.
TU.
That's why I said ATU. It sounds
ATU.
more
patriotic.
Deliberate. Yeah, ATU. Okay. Part of the ATU club.
Good luck with that, Steve.
So I'm familiar with U factor from a Fenestration Council sticker method. So let's start there. Why do they use that instead of R value?
Yeah, so there's actually a couple answers to this, but the first one is that we use R values because people like the idea of more is better. So because it's resistance to heat flow.
Because it's a bigger number.
It's a bigger
Unless
number.
you're Mies van der Rohe.
I hate to do this. Who's Mies van der Rohe?
Oh, Peter, come on.
Peter, one of the most notable architects ever, who said, quote, "Less is more."
I'll do you one better. This photograph back here behind me, Peter.
Oh, nice.
Is Mies van der Rohe's Lakeshore Drive Apartments in Chicago that I took that picture because I love that building.
Okay, now maybe somebody else should take over
that's
at
how
this point.
Disappointing. Just kidding. Go ahead. So you were explaining basically the math behind why we use R value, or the psychology behind R value.
Well, here's the crazy thing. We need to use the U value because, that tells us how much heat the building is losing or gaining to size mechanical systems. So the R value is more of a marketing thing, except that the crazy thing about the reciprocal relationship between heat flow and resistance is that if I want to know the total heat flow through a building, I need to convert to R values to add those performances together and then flip it back at the end to U value. So you can't add U values, but you can add R values. So there's both a marketing reason and a technical math reason as to why we sort of need both numbers.
But the math reason is purely that's the way math works. It's not it changes it's a understanding from would it be algebra direction?
Yeah. And the other thing that's interesting about this is that the U value is a rate, right? It's BTU per square foot per hour per degree Fahrenheit temperature change. And we should thank our lucky stars that heat flow is a linear relationship and not a curvilinear, right? So that makes our lives a lot simpler. If we add more insulation, it's very easy to calculate the new heat flow as opposed to it being a non-linear relationship. So we're lucky that type of heat flow is mathematically relatively. There you go. Physics, we should feel lucky.
I don't feel lucky.
You look lucky.
You also brought up a very basic point that it's a marketing ploy on some level.
Oh, I thought you were going somewhere with that joke.
It is easy to quantify. It is easy to go, and maybe that's because my brain's been trained since I was a kid, and the first time that my dad explained to me that fiberglass bat was an R13, but if we used the mineral wool, we got an R15. Mm-hmm. That easy to equate number that we're able to just apply to everything makes perfect sense. You know, it is understandable to just go, okay, well, we added this per inch, and then we can just do that math very quickly. One of the things that we do when we do that sort of math is that we completely just push to the side glazing and framing and things like that. And I think one of the things that Steve brought up earlier was the idea that we just go, oh, well, we build a house with an R60 wall and think that automatically means that we're building something of quality. That was me teeing you up, Steve. Now it's your turn.
Oh, sorry. I didn't realize you were talking. Yeah, so I'm busted on you. Yeah, it's a pet peeve of mine when I brought it up, right? The whole, we build R60 walls, we build R40 walls. So let's go back to our control layer podcast. And if you haven't listened to it, I suggest you go back there and listen to some of these, because some of it, this information builds on those.
Some of it, not all of it.
Not all of it, exactly. Not the parts Jake speaks of. Anyways, the thermal control layer is number 4 on the control layers for good reason, in my opinion. Right? Like I said then, it's a financial equation. Put as much insulation in there as you can afford. That performance doesn't necessarily equate to high R value, right? Just because someone says, I build R50 walls or R60 walls, whatever the number is, if they have an air leakage rate at 3.0, then what does it really matter? And this gets back to where I was building my case with you, Peter, when you were talking about it's conduction, not convection or air leakage, right? If I put a fluffy insulation, or let's just take say a 1980s roof detail. I put an R38 bat in the attic underneath a air spacing flute there, right? The styrofoam flutes.
A vent chute.
Vent chute, yes, thank you. And then I pack in an R38 in the eave, but I leave the R38 exposed at the end. Well, the air that comes in through the soffit, how does it know that it shouldn't go through the butt end of that fibrous insulation and only up the chute, right? So it's a detail that the insulation gets wind washed, which significantly lowers the R value of that. So
are you making an argument that having a well air sealed and well air managed home is going to make your insulation perform better?
Well, I think my argument is if you really want to impress me, then sit down. Let's talk about what kind of windows you're using. What are your air sealing tactics, your water management tactics? And the last sentence of our conversation should be, we usually do an R40 wall with an R60 lid. And if you end the conversation that way instead of starting the conversation, then I feel you have a better understanding of what you're doing.
You know, when I first started to work at the NHB Research Center in 1993, the NHB Research Center has a testing lab. And I remember going back to the testing lab and watching how they tested a fiberglass bat in a guarded hot box. You know, in a guarded hot box there's a heating plate underneath, and you put in a certain amount of energy, and then you measure the temperature, across that from the top of the lid to the bottom of the test box. And that tells you, how much heat has made its way through at a given rate. But the really cool thing is that when they cut the bat to put it into the guarded hot box, it has to fit exactly into the box, right? And then you clamp down the lid, which is a double gasketed lid. And I'm thinking, So I only get R13 if I put it in the framing
If it's
cavity
in this assembly.
exactly the same way they put it in this guarded hot box. And absolutely nothing could be further from the truth. So, the difference between air permeable insulations and air impermeable insulations, it's a lot of night and day, because while in the guarded hot box you're testing just conductive heat flow, the rest of the world, that's not how it works.
And it's my understanding that R value that's applied, that rating system is kind of devised by the people from fiberglass industry first, right? So it might not be a fair, for what you're saying, it's not necessarily a fair rating system for non-air permeable insulations, correct?
Well, if it's pretty hard in a laboratory test like that to measure both the resistance to heat flow as well as airflow, right? So it's just an inherent performance difference between the two materials. But you bring up another issue, which is the temperature difference that you choose to rate the material, right? It can affect the performance of the material. And so the way that we test is not necessarily the same way that other countries set up the standard for the testing of the material. I don't know how much that standardized test was driven by the fiberglass industry, but would not surprise me to learn that's the case.
What's interesting about insulation too, it's that the more sloppy it gets installed, it's arguable that probably lowers your risk, right? I was trying to think this through while you were talking, but the more intricate and detailed I am about my installation, the less forgiveness I build into the system. In some cases, I think it can go both ways, because you can obviously open it up to air leakage and get moisture-laden air to cold surfaces, but like a bad cavity insulation job, there is some risk there, but the obvious benefit is a crappy, fluffy insulation job means I have a lot more energy hitting the surfaces to dry them out.
That's a really tricky question, Steve. But you're, the balance between resistance to conductive flow and resistance to air leakage, it's not a game you'd like to play, right? To find the sweet spot where, hey, if I introduce enough lousy installation, I actually get enough heat moving through the assembly to keep myself out of trouble. Like that's a pretty dangerous game to play. Yeah. Why not just
but it's not like water management, right? If I screw up water management, my risk elevates exponentially. Whereas insulation, I don't. And I think that's, again, part of why it's number 4 on my control layer list of 4, is just because of that it's least likely to cause a problem if I solve for all the others.
That's kind of a conversation that our industry has about houses that were built 50 or 100 years ago, that is related to air leakage, but it's also related to insulation, that when there was no insulation in the walls. I actually brought this up in our pre-discussion here. The house that I'm in right now was built in 1965. There is R7 insulation in the kitchen and the bathroom. The rest of the house has no cavity insulation whatsoever.
Hey, Peter.
And it has no problems. But we make the wall thicker, we dump a ton of insulation in there, and we stop air movement, and now all of a sudden we have a completely different beast that doesn't have that potential drawing caused by thermal movement and air, right? That's the same argument that Steve's making.
Yeah. I'm going to make up a new word and ask Peter about his BSopedia. It's like the Wikipedia of building science. So in nice. Peter's BSopedia, do you know of anybody that has, I'm trying to think of how do I phrase this question, compared R value to air leakage? Like if I go from an air leakage rate of 1 to 2, what would be additional R value enhancement to negate that level of air leakage?
Well, so the crazy thing about the craziest thing about the difference between conductive heat flow and convective flow is that conductive heat flow is pretty much, as you describe it, a proportional relationship. And it's not a proportional relationship with air leakage, right? Because air leakage is way more complicated than heat flow through solids. It depends on the size of the holes. It depends on the temperature difference. The temperature difference inside to outside is governing flow of both conductive and convective energy movement, but the configuration of the holes on the inside and the outside and the air leakage pathway are incredibly complex, right? And have a big impact on how that...
Yeah, I mean, there's tons of variables, but nobody's done like just a general sense, like, 1.0 of air leakage on a 2,000 square foot house is equitable to, R10 of insulation.
It sounds like an extremely difficult question to answer.
Well,
that's what, Jake, that's what I do here. I dig deep.
Well,
I mean, maybe
so when we do
consider it as an example.
When we do heat loss and heat gain calculations, it's pretty. We can equate that, right? We have equations for calculating UA, which is total conductive heat flow, and we do have equations for how much heat gets carried by leaking air. So yes, we can do that.
I mean, you could just take any one of the modeling programs and change the air leakage rate from 2 to 1, and then diminish your R value till you get to the same BTUs.
Right, and we do know that in most typically cold climates, about 25 to 40% of the total heat loss and gain can be attributed to air leakage. So it's anywhere between a quarter of your worries in terms of BTUs, or up to 40%, right? The moisture moves with that leaking air. There's really no moisture penalty in just conductive heat flow, right? Unless you get condensation on the surface that's cold, which is exposed.
I guess what I'm getting at is, and I'm going to use Jake because he's an exceptional air tightness guy. But if Jake builds a 2x4 wall with R6 on the outside at an air tightness level of 0.5 and then pays AeroBarrier to come in to take it under 1.0, is that a better performing house than someone that builds a 2x6 wall with 2 inches of polyiso on the outside with an R3 air leakage?
So from a straight energy perspective, yeah, that calculation's pretty straightforward.
Yeah. It'd be interesting to see which one of those is. I mean, here it is. I do some, pretty high R value walls, but now I'm making an argument for the 2x4 with R6 on the outside.
No, you're making an argument for good air sealing.
Yes. Yeah, and that really, that's why it's number 2 on the control air list instead of number 4. That I think it makes a difference.
I think it's also important that the listeners note when Peter says, well, we know, I think what he's saying is Peter knows most of the time. When Peter says we know in a group conversation, I very rarely go, oh, yeah, I knew that already, too. And just shake my head. Yep, we do.
It's funny because I've been asked several times, well, where did you get that number 25 to 40%? And it's actually kind of hard to trace, but I know for when I was working for the NHB and developing their building science course, it's a DOE generated number, and it's based
25 to 40%.
I pulled the air leakage number out of thin air. Like, what could be more
appropriate? So what's thin air? What's thin air? Why do people say thin air? Why don't they just say I pulled it out of the air? Why does it have to be thin air to get the number?
Because the person who first said it was from Colorado, Denver, Mile High.
It's that whole British thermal unit.
No, it's thin air there.
It's thin air. Yeah, exactly. He was on top of a mountain. Maybe it was Moses that was the first one to grab it out of the air.
This is quite the
top
path
of the
that we're on.
mountain.
But
So it was
interestingly,
thin air.
when you do the heat loss calculations and you're trying to figure out, like for a forced air system, you have to change your calculations for the density of air from the seacoast to Denver, because thinner air has fewer molecules, which means you have less matter to transfer the energy. So you actually have
Less bits to bounce around.
Yeah, you have.
So if I buy an RV, how do they calculate what I should have? Because they don't know whether I'm going to be camping in Colorado or San Diego.
They just want to sell you one that's got a
the
good price tag.
the heat loss through the RVs is not something that they're.
That thin air
Optimizing.
conversation, though, is the same reason why my frozen pizza comes with an alternate cooking method for high elevation, which is interesting.
So, yeah, I'll take the blame for taking this down the wrong track. So let's get back on track. One of the interesting things, I've told this story a million times, but because we're talking about R value, I'm going to tell it again. You know, as a young architect working at Building Science Corporation, I had lunch one afternoon. Gus Handegord was at the table, and him and I were sitting there. Gus Handegord, for those of you that don't know, was one of Joe's mentors, Joe Stiebrick's mentors. And Gus wrote books on building science and blah, blah, blah. But anyways, yes, Gus is a pretty smart guy in the building science historical world. Anyways, young architect sitting there saying, hey, Gus, lay it on me, man. I'm a young architect. Give me the inside track. What's the best wall I can build? Like if I was designing the Handegord dream house, what's the secret sauce here? He says it's real easy. Put as much rigid insulation on the outside of the frame as you can afford. You'll never go wrong. So let's talk about that.
Which is where Joe's perfect wall came from.
Which is where Joe's perfect wall, and I mean, everything that we argue is always for continuous insulation, right? It's like saying the fat on your body is a better insulator than the jacket around you, right? No, it isn't. The jacket around you is always better. And if you don't believe in continuity, then I suggest take that jacket and cut 2-inch strips out of it every 6 inches and see how well it works for you. I was looking for an old shirt. I was going to do an Instagram video on that.
Oh, nice.
Hey, look at this is how we treat our houses. I got to find the right jacket that I don't want anymore. But yeah, it's
you won't wear it after you cut holes in it?
Well, I might. Who knows? It could be, I'll get an R embroidered on the back side of it, and it can be the new thermal wear. I could start a whole new.
I think
just to make sure everybody's following what you're saying with cut those strips out of it. Those strips would be representative of the framing members that we have.
Yeah, that you offer some opacity or some less R value.
Because that R value of wood is like R1 per inch.
It's a 1.257936.
You totally made that up after 1.2.
I did.
Yeah, out of thin air. It's like the statistic. I read that 75% of statistics are made up on the spot.
Well, I don't call it statistic. I call it authoritative lying.
Yeah.
Because you
speak
have to be
clearly,
smarter than the
speak
person
loudly, and be
saying
the
it
first one to speak.
Object. Yeah. First one out of the chute is usually the one people adhere to.
So while we're talking about Building Science Corporation and insulation, I think that the original way I learned it was this is the starting recommendation for a net zero home. They're 10, 20, 40, 60, and 5. Isn't that what it was originally? Net zero is the way that it was sold.
I don't know if it was net zero. I mean, I just call that the stepping off point, right? I think that's where, and Peter certainly correct us with the BSopedia, the stepping off point, meaning that this for a cold climate is what makes sense financially, thermally, comfort, health, building science, blah, blah, blah. It's kind of that should be your baseline and migrate from those numbers.
And it represents proportion and it represents restraint in areas that restraint is important, or less insulation is important. Can we go through what 10, 20, 40, 60, and 5 means?
And I would just add to that in my no fuss way, it eliminates stupidity, right? Meaning that I know people that I do R70 walls, and then it's like, wow, that's great. What kind of windows? Oh yeah, I got these great windows from a local aluminum manufacturer that we use. He does a great job, and they're, R2. 0.35 or something U value, and they're putting those in R60 walls, which is stupid. But yeah.
So 10 for below grade, R10 for below grade, R20 for above grade.
When you say below grade, I would just clarify that as sub slab.
Oh, I'm sorry. Yeah. I should start over again. 10 for sub slab, 20 for below grade, 40 for above grade, 60 for the lid, and R5 for the windows. So that's 10, 20, 40, 65.
Right.
And those are proportionate, handling the delta T, the temperature difference across the assembly between inside and out. So if we're looking at the 10 or the 20 number, you're dealing with ground temperature versus interior temperature.
Yeah.
If we're looking at the 40, we're dealing with exterior temperature versus interior. 60, especially if it's a vented assembly, we're dealing with the temperature difference between attic and interior temperature. And then that R5 number, I'm assuming that when all this was started was like a R5 is just about as good a window as you can get in North America and not have to pay an arm and a leg.
It's kind of the cap R value for a dual paned IGU. Yeah. But
I'm going to take charge here for a minute.
Steve, can I just say
he
one
means
thing
interrupt.
quick?
The minute I say I'm going to take charge, he has to interject. Can I say something in front of him?
I'd like to hear
ahead.
what Peter has to say.
Go ahead.
Just want to say that Steve said the operative thing here, which is for a cold climate, because if we're arguing for insulation values to be proportional, they're proportional based on your climate. And the actual BSC article where this is codified, this 10, 20, 40, 65, is called zeroing in. So it was Joe, as an engineer, weighing in on what he thinks is the best way to get to net zero for the building enclosure performance for a cold climate.
All right.
Now take charge, Steve.
No, that was good. That was good. I'm just busting on you. But I think it's really important that this is a huge topic for all of our listeners and for me. And I think we should go through each one of those steps and each of us give our kind of pro-con. So let's talk about sub-slab, right? Obviously, and I'll give you my take and then I'll let you guys chime in. Continuity across the slab, I think, is very important. And I think that it should be done. That being said, when you're up against budgets, the sub-slab insulation is pretty easily retracted to the 4-foot perimeter of the slab, and understanding that the perimeter of the slab is probably the most important sub-slab insulation there is.
Why is
and
that?
The other thing to keep in mind is that the delta across that is maybe 15 degrees, right? So if I had to give it up, that's probably the insulation that I forfeit the soonest and easiest of all.
Why is the perimeter more important, Steve?
Because that's where it's at its coldest, and that is where you are most likely to get, discomfort around the perimeter. And
you're saying at its
the
coldest,
thermal bridging and isolation.
But Steve,
at its coldest, because it has the least of its own material around it. It has the least contact with our interior
it's concrete
air.
slab pretty much touching the concrete wall, touching the ground.
Yep. Okay.
As opposed to sitting like on a stone bed or something in the middle of the slab. Yep.
Just
and
clarifying.
I think you'd agree, Steve, that the real reason we put R10, even though there's only a delta 15 temperature between the basement space and the ground, is to elevate the surface temperature for both thermal comfort and indoor air quality reasons.
For my Tootsies?
I hadn't thought of it that way. I'm having a hard time with the image in my head right now.
I'm just blocking that imagery out. Just plain and simple.
I'm not sure what you two think the word Tootsies meant in that sentence.
I have no idea. But that's what I'm saying.
We'll leave it at that then. Okay, so then we continue up the wall. Why is the wall different than the subslab?
And we have we have the wall insulation, which I'm going to go on record saying I don't understand exterior insulation. I know there's a lot of people out there that claim that that's the way it should be done, but I don't buy it. I run my insulation up the inside of the wall always and every time. I like it there. It is the less expensive option, I believe. I also, a lot of builders like it because it's rainy day work, right? That's something that you can do sometime in the first 2 months of the project. There isn't a specific date to it. It's like, hey, we're getting rain Monday and Tuesday. Why don't we get some 2x4s? We'll frame those walls up and insulate the basement, kind of thing. The one thing that you might be able to help me out here, guys, with is the exterior insulation. I remember going up to the beautiful state of Vermont and visiting a passive house at the time that had 6 inches of XPS on the outside of the wall. Now, that wasn't the concerning thing to me. The concerning thing to me was there was about 2 feet of water coming up out of the 8 foot of the foundation wall. So the insulation's literally standing in water, in groundwater. So how the hell is that insulation even working with
it's got conductive water
if
all
you got
around
conductive water taking ground temperature right to the concrete and circumventing the insulation on the outside?
Isn't the answer for the most part it's not? It's simply not working? Or it's
that's
reduced?
Part of my argument is, and I've had this conversation many a times with a lot of people, and I've never walked away saying, okay, that makes sense.
Well, if it's EPS, which is expanded polystyrene, it's like 75% open cell, 25% closed cell, and that 75% means it takes up water pretty readily. So yeah, that means 75% of your air pockets are gone and they're replaced by highly conductive water pockets.
And the air pocket is the resistance space.
Yeah, I mean, the only thing that's a better insulator than air is no air, right? So a vacuum is a better insulator than an air pocket. And the smaller you make the air pockets, the more resistance you get. But the long and short of it is that 75% open cell means EPS takes up an awful lot of water compared to, say, XPS. But it does give up the water very readily, right? So, yeah, it'll fill up with water and its R value is eroded. But EPS also, releases that held moisture relatively quickly when the conditions change. So, yeah, I think what you're describing, Steve, is that if I could keep the insulation dry and I could protect it, we all know that continuous insulation on the outside of any assembly is the perfect wall concept, right?
Well, the problem too is when you look at a wall section, I can provide absolute continuity under the slab, up the perimeter, and up the inside of the wall. If I jump to the outside of the wall, then I have the thermal bridge between the footing and the bottom of the foundation wall.
But that thermal bridge is way less important than the thermal bridge if you run the insulation up the inside of the below grade wall and then run your continuous insulation up the outside of the above grade wall. You've got a discontinuity there. You've got to move from the inside to the outside.
You make that connection more complicated.
You do. But
okay,
he doesn't want to admit that.
So here's my argument there, though. I make that connection more complicated, but there I have the benefit of making that connection R60 if I wanted to, pretty inexpensively and easy.
Okay, you've now crossed from a strictly thermal conversation, right, to a buildability and
Well, that's what I
cost.
talked about. I said we're going to go up and we're going to talk about all of our aspects. So everything is on the
Don't
table.
remind us what you said.
Well,
like you're
and,
gonna
and
be right.
when you mentioned 6 inches of EPS on the outside of a passive house below
Do I
grade,
need to play this back? Do I need to play back here?
You could have said anything there because I wasn't listening.
I know. That's all right. I'm ignoring you.
yeah, Steve, I completely agree with you that there are a whole bunch of really solid reasons for protecting that insulation below grade by having it on the inside. And you know, this is a conversation that at Building Science Corporation changed over the period of time that I was there, I think, where Joe was moving towards, yeah, there's physics benefit to having that continuous insulation on the outside of a below grade wall, but it's just not working from a practical
Well, and then
standpoint.
you have all the whole issue of bugs, rodents, all that stuff
Yeah.
that Jake I know is going to have a story. And then my particular pet peeve with it is, how do I treat the insulation when it breaks grade
Yeah.
for the last
How do you
10
protect
inches or 12 inches of the foundation?
But that brings up Jake's original question was, why do we move from R10 to R20 when, you know, if we're down 8 feet below grade under the slab and it's 55 degrees and we're now on the vertical part of the bottom of the foundation wall and it's 55 degrees there, why do we move from 10 to 20? To me, we moved because we're now going to be moving up that below grade wall, and the wintertime soil temperature is going to be dropping as we move up. And then when we get to the above grade portion, you've got a highly conductive masonry material and no opportunity to insulate inside the material. You gotta really up your game for the above grade portion of the below grade wall. That's the real.
So Steve mentioned that I had a story, and I've told the story on the podcast before, but I think it goes well with our put the insulation on the inside. We built a turn-down slab house for my parents in the late 90s. When they sold it about 8 or 10 years later, the inspector said, you got to pull that metal trim coil and the insulation behind it off on the outside of that foundation so I can inspect that insulation, or
No
so I can
kidding.
inspect that foundation. And so we pulled the metal trim coil that we had bent very nicely over the EPS or XPS to protect it, and the XPS was mostly gone. It had been eaten away by insects. There were snake skins. There was mouse poop. And not only had we thought we had done a really good job protecting it with the brake metal, it was gone, and the brake metal wasn't even in that great a shape even after 10 years, too.
All you protected was the crime.
Yeah. All we did was make it a more inviting, habitable space for things that we don't want living there. And, you know, you think of it as like, oh, well, it's above grade. It's not going to have insects and stuff in it because they're not going to want to be exposed in the winter. Well, they went to the inside face of it, and they were thermally coupled to a heated and conditioned slab. So it was a really inviting place that had potentially some moisture coming down off the walls. It had temperature. It had everything that they were looking for. And it really, when we pulled it off, I was just like, oh, well, we're never going to do that again.
And easy to chew.
Yep.
So what if I switch to a rigid mineral wool as the exterior below grade wall foundation?
Certainly less inviting, for sure.
But you still have the aesthetic question. You
still
still
have to
have the
protect
water table question.
Yeah, I kind of set that up for you guys, but I still think that even though the advantages of exterior insulation continuous are compelling, we just have not figured out how to make it it's not just the aesthetics, it's how do you get the plane of the below grade wall to somehow match up with the plane of the above grade wall. If you put, I mean, how many inches of rigid insulation, let's say rigid mineral, would you have to put to get to R20? So how many, that's like
Yeah.
R3.8.
Yeah, 6 or 7.
That's not
like-
feasible, right?
No. And you know what's funny, Peter? When I did the first passive house in Massachusetts, 11 years ago or so, the guy I was working with, the passive house consultant at the time, we started out with, okay, we'll put 4 inches on the outside of the foundation. And then like a couple weeks later, he's like, okay, I ran the numbers again.
Yeah.
We really need to up that to more like 5 inches. And then, a little time later, we really should be looking at more like 6 inches out there. Finally, I just said, Mike, I cannot go to a builder and start talking about how we're going to fasten 6 inches of rigid insulation on the outside of a foundation wall. I mean, think about that rodent hotel, right? I mean, they could chew on the inside layer and have a hell of a home there. And how aesthetically do I hide it?
Yeah. How do you line it up with the above grade structure? And what do you do at entryways? I mean, it just doesn't work. Now, when we get to milder climates, because I remember having this conversation with, I think it was Coda at Building Science Corporation about, there are climates where decoupling the slab or the foundation from the soil, like at climate zone 3, how much of an energy penalty is there for how much insulation you put? And I remember Coda, I think, saying that in climate zone 3, that there was about a 10% energy penalty for the sort of the total energy consumption of the building for heat loss in climate zone 3 for that, say, 8 to 10 inches of a perimeter of a slab at the perimeter, that if it was uninsulated, you would lose there.
Because the delta T between the ground temperature and the building is so small.
Yeah, well, in this case, if it's exposed above grade, it's the air temperature. The air temperatures are not getting low enough. But the thermal comfort and moisture issues for that type of a thermal bridge, sort of overwhelm. Like, no, you can't. You may be able to justify the 10% energy loss, but the thermal comfort at the perimeter of the slab and the low surface temperature, that can promote things like dust mites and mold and so on. So again, when we answer questions strictly about R value, we always get into trouble because performance is never about just R value.
Well, I think that's the BS about BS, right? That there's parts of building science that, even though laboratory true, aren't really livable.
So, Steve, is the BS of BS, is that BS squared mathematically?
Ooh, the BS squared comments, I like those. BS squared. It's the BS of BS. It's when we take it too far. So let's move to above grade walls.
40.
Above grade walls, R40. My rule of above grade walls is that I strive for about 25 to 30% of continuity in insulation on the above grade wall.
So you're making an outboard argument now?
I'm making an outboard argument that I listened to Gus, and I, out of respect for his knowledge, I still hold that statement very, very true. Which is interesting because I just had a client, I don't know if I got the job, but he wants to build an all steel stud house, which I've never done before.
Ooh.
But that changes the dynamics of
in
insulation.
In your climate, Steve?
No. This is probably climate zone 3.
Yeah. Okay. Well, that's going to be easier than climate zone 5 for sure.
Certainly.
Yeah.
Certainly. But yeah. So above grade walls for me, R40 plus or minus, and here's the kicker for me on above grade walls, because windows usually occupy at least 15 to 20%, even on a common house.
Sure. Yeah.
I would rather put more money into the windows because there's an energy efficient part of that equation, but there's a huge comfort part to that equation.
Well, they're the 5 in this equation.
They're the 5.
And
so if I could take that 5
by far
and bump it to 7, then I'm okay with the wall being 32.
Yep.
So
moving that insulation outboard, you're getting higher R value out of it. You're warming the wall, changing the condensing surface of the wall. You're managing.
I'm warming 80% of the wall instead of 65% of the wall.
You're managing for that vapor condensation that we talked about in the vapor episode. It's a gas, as Peter would say. And we get a lot of just general benefit by changing the location of the insulation. And I guess technically we're paying for a little bit more, but our installation's probably cheaper because we're not cutting it to fit in between each one of those cavities. So like, I really don't see an argument for not putting continuous insulation on the outside of the wall from a health, comfort, durability, installation standpoint.
Right. But you know what's interesting is, you know, Zip has the Zip R board. So we have manufacturers that made this real easy for us. Now, for those of you that build extreme high performance homes, I know you're going to say, okay, maybe our Zip just doesn't do enough or whatever. But as a commodity solution to a thermal problem, that
eloquent.
is an outstanding material, right? Because all across the country, I can build 2x4 walls and put R6 on the outside, and have a hell of a wall if I manage the air tightness along with that.
Peter's having a zipper fit. It's cold in Vermont today, and we're talking about
well,
insulation.
not only
I was going to say, this is all about
What's
our
what's the
value right
thermostat at, Peter? 52?
It's the zipper on his shirt before anybody gets a...
I'm sorry. I'm really hypothermic. I've lost my mittens, and I don't care.
I've lost my mittens.
This is standard Vermont joke. I've lost my mittens, and I don't care. I must be hypothermic.
I can see the...
So
that would be a
it's
joke in
interesting to hear
Vermont.
this conversation about continuous exterior because, you know, Steve and I, being, you know, cold climate guys primarily, we sometimes get hammered for like, yeah, but you guys always talk about, you know, the whole world as if it's cold climate. And so I would argue that even in Houston, which is climate zone 2, or
I
Dallas,
love where
which
he's going with this because
Climate
I
Zone
got
3.
a beautiful
I
compliment.
still think that continuous insulation is a good idea in those climates. The benefit may not be as great from a thermal perspective, strictly thermal, but there's a whole bunch of other reasons it's a good idea. And interestingly, even in Houston, the second largest insurance claim is frozen pipes. And the reason it is because people in cold climates would never put plumbing pipes where people in Houston do. So if it does get below freezing and you want to build a building for design conditions, you're still going to have to deal with some, you know, moderate heat loss issues, even in Houston.
You know, Peter, I always explain it when people say, well, what about like warmer clients? I know you live in Boston, but what about, you know, other parts of the country? I tell people, for
Is that
me,
the voice they use?
It's unbelievable. The equation for me is simple. You buy energy and you want to convert, or well, you don't necessarily buy energy. You want to convert energy to a useful energy as cheaply and inexpensively as possible. So solar panels, obviously, if the sun comes up, I buy the solar panels, I convert the solar energy into either heating or cooling, or I turn it into electrical energy and then that changes it to heating or cooling, blah, blah, blah. I'm not going to get into that crap. But you want to convert it as inexpensively as possible. So now I have a house with a certain level of energy that I bought and paid and converted it to. The second part of the equation for me is hold on to it as long as I possibly can. Well, your argument for Houston is, in my opinion, spot on, because I've paid for a certain amount of energy to convert it to a cooling energy. And I want to hold on to that cooling energy as long as I possibly can. And regardless of what climate you live in, heat is moving across the wall. Northern climates is moving from the inside out. In southern climates, it moves from the outside in. But in either case, it's challenging the converted energy that we bought and paid for. Yes, I know. The plumber was just here to fix the shower, and they just heard him go out the door. So they're
the long and short of what you just said is the R value is the resistance to the conduction of heat. And we're worried about that temperature being, or that heat, no matter where we live, just about, unless we go to San Diego.
Well, it is important that 10, 20, 40, 65 rule is for cold climates, but it doesn't mean that you give up all rules and proportions when
Doesn't
you
mean it
move
doesn't
to a
apply
heating
on
to
some
a
level.
climate like Houston. The other thing that's interesting to me is that we haven't talked about windows, and I know we're going to do a session in 2021 that's all about glazing, because
Oh my God, I'm not going to be able to sleep now.
Peter's giddy.
no that Steve said that after I go after the R value of the opaque wall, I immediately shift to the next weakest link, which is the glazing. And the same is true in cooling climates, but for a whole different reason. It's all about trying to keep that bloody sun out
Condensation.
rather than getting it in.
Yeah.
So the windows don't become any less important in cooling climates. They just shift the property that I'm most worried about in my glazing.
You bought and paid for that converted cooling energy that's in your house. You want to challenge that converted energy as less as possible, as least as possible. And better windows will promote less challenge.
I'm actually working on a blog with Ann Edmonster right now that's going to involve window performance, and there's the most complicated product that we work on is glazing. I mean, it's just incredibly complex, and we say R5 as a thermal performance of window. We can't really move from R5 to the next step up. It's just this huge jump to R8 or R10 with triple pane sort of quote unquote passive house windows. And that's a big problem in our industry, that between R5 and triple pane passive house, there's nothing to fill that gap. You're at U value 0.2, and then, we can't push double glazed windows much further without jumping to a whole different window product.
And
that's
for
a
some
big
reason,
problem.
American manufacturers are not interested in triple glazed.
Well, I wouldn't say American manufacturers, because this was a comment I made about on the Fine Home Building Summit yesterday that I typed in. A lot of what we do are cultural expectations, right? Window manufacturers don't care about triple glazed windows because we as architects and builders
Generally don't
tell our customers they should be concerned about it. So in turn, the people we serve don't care or aren't educated enough about it to force a change. Right? It's one of those things where for 80% of the crowd, double glazed is good enough.
Well, and the payback, if you're doing that silly net payback calculation to justify it by energy performance alone, it's just the payback is like 50 years for anything above a
It is, but it
window.
isn't, Peter, because I just did it, and I'm not going to beat up on anybody, but we domestically priced a window package, and then I priced it out with the Schuco UPVCs.
Mm-hmm.
The triple glazed 0.13 versus a 0.21 window
Mm-hmm.
was about 30 to 40% less in price.
The
And
triple
that's
pane was
including
less?
shipping cost
Yes.
on both. Too.
And that included
No
shipping
kidding.
from Europe.
Wow,
Yes.
that's shocking.
They are very
And the thing
competitive.
Good to hear.
The thing that the homeowners absolutely loved about it, a couple of the windows are now 11'6" by 6'6", and they're a piece of glass.
Yeah. Well, if you can get up, so 0.13, that's strong R7. Now you're getting into levels of performance where, because of the heat gain you get in a cold climate, you're rivaling the performance of some opaque walls, right?
Yes.
Because the opaque walls, don't let in that solar gain that you can get. Hey, I know we're running a little
Too much
bit long.
on Windows. Let's go to
Well,
let's
we're
go
gonna
to
come back
60
to that
after this.
But I want to go to the attic, because why would we move to R60? Is the heat loss from the attic any greater or less than the above grade wall? Why do we say we should be R60 in the attic?
Okay, so I'm going to jump off the ship and say, yes, it is, right? Stack effect in that suggests that. And when you run, I want to say when you run the heat calculations, at least what was that one that we used to run all the time that Coda ran and the other guy, Phil ran?
Well,
they just would do rem rate.
Rem rate. Yeah.
Right? Because rem rate would put out a report that would proportionally lay out heat loss. And once you got past windows and stuff, the ceiling always had a higher heat loss per square foot than the wall did.
Yeah, but Steve...
with the same R value.
Right. But that's assuming that because of stratification of air, the surface temperature on the inside of the assembly was significantly higher at the ceiling on the top floor than it was on the wall. And you know
more heat to lose.
Right, but you know if you design your system well enough that you don't really get that delta T there. I think the real reason is we put more insulation up there because we can, right?
Well, and I was just going to say, that's, for me, I always up the windows, and the R60 usually goes to more like R70 or 80. Just because my insulator said, Steve, he goes,
yeah,
you make us drive a truck to the site. We fill the hopper. The guy climbs in, drags the hose all the way up to the attic. It's pennies to spray another 6 inches of cellulose up.
But if you build the ceiling the same as the walls, in other words, you cathedral the process, and you don't have that huge free space of an attic, now the whole equation changes a ton, right? Because the cost
space
of
available, the type that you're going to have to
use, the whole
use,
set of parameters, and all of that.
The other thing about Steve's argument about it costs pennies, the thing with that is the majority of insulations that we put in attic spaces are by far the cheapest per R value insulations. It's cellulose, it's blown in fiberglass.
Yeah.
Like that's just, it's not, we're not filling that space with EPS that's cut to fit. We're filling that with just send somebody up there and have them blow around.
So I just got to tell you this really quick story about when I built the Sips kitchen addition at our house. So the floor, the walls, and the cathedral slope of the shed addition, they were all R38, right? They were 2x8 panels. And so we had polyiso in there, the highest R value we could get. So I got an R38 floor, an R38 wall, and an R38 roof. And my wife comes down in the middle of the winter with a cup of coffee, and in her very thin stocking feet, she walks from the kitchen that's over top of the basement to the kitchen floor that's over top of the Sips. Now remember, I built this on piers. So she's walking on an R38 floor. And she turns to me and says, okay, Mr. Building Scientist. And I know whenever she says that, I'm in deep trouble. She said, explain to me why you built this energy efficient addition and my feet are cold over top of the Sips addition compared to walking over the basement. And I said, well, the answer is that if you walked on the walls or the ceiling, the temperature there is exactly the same. And she says, that's exactly the half-assed answer that infuriates all of us who don't give a shit about what the heat loss rules are. What we want is a thermally comfortable floor. So I totally blew it. So it's not just about R value, it's about performance.
Mm-hmm. Yeah.
Peter, does your wife listen to the podcast? Will she hear you tell that?
Are you
recant
serious?
That story?
My daughters and wife learned that the name of this was the Unbuild It, and they were like, oh, geez, what, you guys? What the hell? I thought you were a builder, not an unbuilder. So, yeah.
I have Friday night date night where my wife and we listen to the Unbuild It podcast, and then we watch some of my videos.
I know, Holly. That is the biggest crock I've ever heard in my life.
Well, I can say that I don't know that my wife has listened to or watched anything that I've produced. I know she hasn't read any articles that I've written or anything like that. Every once in a while,
I do get
Instagram.
I've ever listened or watched anything you produce.
So I think we ought to do an episode where our spouses are seated right next to us, and as soon as we start to talk, they go, wrong, lie, misinformation. It would just be constant.
I'd rather have the world think she exists.
My wife tolerates what I do. She doesn't embrace what I do.
So our takeaways are: R value is the inverse of the U factor. The U factor can be slightly more informative. R value is the resistance to conduction or conductive heat loss or heat movement. 10, 20, 40, 60, and 5. And don't put the stuff on the outside of your foundation. What else?
Put it on the outside of everything else.
I mean, proportional is key. I think the place where I would be the least reluctant to maintain high levels of proportionality is just using better windows, because just moving that window closer to the wall, R value, is always a good thing. But being proportional, I think, is huge. And I think don't get caught up in R values is my takeaway. I mean, use them, but use them, keep it a safe distance away from you.
Part of a system.
Start the conversation out about water management, air leakage, and let the last couple sentences be about the R value you use in the house. Don't start the conversation with that.
Yeah.
Closing thoughts?
And just that it's never just about the energy associated with that R value. It's thermal comfort and indoor air quality as well.
Good wrap up.
Cool.
Okay, this has been Peter introduced it in a way that I thought, that's the title. This has been UBIP R rated.
Oh, nice.
Thank you for
I don't get it.
Thank you for listening today. We enjoyed this one. This one was the last in a let's call it season 1 on the
nice.
control
season
layers.
1. Yeah.
We want to encourage you to send your questions to questions@unbuilditpodcast.com. I'd like to announce that we have stickers back in stock, so message the Unbuild It Podcast on Instagram if you'd like stickers. And not to insult the intelligence of our audience, but if you were requesting us to mail you stickers, you should probably also give us your address. I think you'd be surprised how many people just said, I'd like some stickers.
Hey, did we spring for acrylic adhesive on our stickers?
Yes, they're pressure sensitive as well. They're PSA.
Next year we might come out with a UBIP roller.
Ooh, I bet we could get Huber to get us some rollers that we could just brand ourselves too.
Nice.
The way that we grow this podcast is by you sharing it with other people. Share our Instagram account with other people. It's Unbuild It Podcast on Instagram. And subscribe to the podcast. That gives us a clear vision of how many people we're reaching each episode and how many people are dedicated to following along with this journey. And leaving a 5-star review on iTunes will help as well. We get more listeners every episode. We get better response every episode, and that's because the people that are listening now are telling other people about it. And we can't say thank you enough and have enough gratitude, because this isn't something that we're advertising anywhere.
Well, and just every month I'm able to create more artificial accounts so I can...
That's why we get more followers.
Yeah.
Hey, Jake.
Get more followers, more.
I just want to close by saying I'm ready for the relationship between heat gain and resistance to heat gain. Are you?
And that's our sign out. We'll leave it at Peter's joke. Till next time, this is the Unbuild It Podcast. Thanks for listening.
Hey, guys. Thanks for listening to the podcast. This is Jake. I'm recording from my truck. We've had a crazy week this week. We had Reisinger and Steve Basic in Columbia recording videos all week. And I'm trying to move. And somehow in the mix, we've also decided to extend the Yeti cooler giveaway. IG is hiding recent hashtags because of all the stuff that's going on with the election. And so we haven't been able to see some of the entries. So I just wanted to remind you that you need to tag the Unbuild It Podcast on Instagram and use the UBIP hashtag and post a video to your page, not just a story, but a video telling us something that you've learned on the podcast. That is our only criteria. We don't even know how we're going to judge it. Do something that Steve likes because you know he's going to have a huge influence. We just wanted to say thanks for being a listener. We thought this would be a cool way to give away a Yeti 105 cooler. This is a $500 cooler, and we even branded it. And by branding it, I mean we stuck a Unbuilt It podcast sticker on it, and then we filled it full of a bunch of sponsor swag. So there are tapes and knives and sunglasses and hats and Huber zip rollers. Like, there's some good stuff in this thing, and we want to give it away to you. You now have until December 19th. We pushed it from November 19th to December 19th. So take the time, make us a video, tell us what you've learned, support the podcast, and we're going to give somebody a really cool Yeti cooler that we ruined by putting a UBIP sticker on. So thanks for listening. Thanks for listening to the podcast, and thanks for supporting us. This kind of thing doesn't happen without the listeners, and we take that very serious. So we'll see you soon. December 19th is the new day.